Okay, let's take a look at some shapes that are quite common in our real life. First, over here we've got a person throwing a basketball. So this picture over here is not that he's throwing many balls, but it shows the path taken by a basketball. Looks natural, right? Doesn't look weird. So when we throw things, they seem to follow a path. Okay, let's take a look at the next image. Here we've got a soccer player kicking a ball, and it follows a certain path also. It is also a curve. Everything looks natural, as it should be. Next shape, we've got a fountain. So when you're at a water cooler, for example, drinking water, we see this particular curve. And we don't find it strange. Over here we've got a bridge, and it is held up. It is supported by some cables. Okay, we see the similar curve again. Another example over here is a satellite dish. Can you find the curve? The similar type of curve. Okay, so all these 5 images over here, they all are examples. They are real world examples of a shape called a parabola. Okay, so right now I'm going to trace out the parabola in each of these examples. So first over here, let's change the color. So here we've got a curve like this. Now in the bridge, here if we were to trace it out, we can actually extend it also. You get a curve. Now in any of these fountains, you can choose any one of them. In the case of the soccer, it's going to follow this path. And finally, for the satellite dish, it's got a parabola over here. Okay, now I'm going to draw in the x and the y axis for each of them. So for example, this could be the y axis, and this could be the x axis. Maybe the y axis over here, the x axis. I'm just randomly drawing positions of the x and y axis. And for the last one, I'm going to tilt it a little. Y and the x-axis. Okay, now in all of these parabolas, what are some common properties? Can you tell that they are all symmetrical? Right? So over here, I can draw a line of symmetry. Likewise, for this parabola, I can draw a line of symmetry. Line of symmetry over here. A line of symmetry. And a line of symmetry for the last case. Notice that for all the lines of symmetry, they pass through a certain point. It passes through the topmost point. So we have a name for this. It is called the maximum point. This line of symmetry also passes through the maximum point. Line of symmetry passing through the maximum point. Line of symmetry passing through the minimum point, the lowest point. And another one, line of symmetry passing through the minimum point. So these are some of the things that we need to know about parabolas. So before this, we learned about straight lines. Now we are moving one step further. We are dealing with curves. So these parabolas, we learned that they are symmetrical. they've got a turning point. So a turning point is either a maximum point or minimum point. Okay, and we also notice that based on whether it has a maximum or a minimum point, the parabola will open. For graphs with a maximum point, we describe it as open downwards. Because we can extend, if you look at the basketball example, we can extend the graph. It is going to keep opening downwards. Likewise for the soccer ball, it's going to keep opening downwards over here. These graphs, they have maximum points. Now for graphs with minimum points, they will open upwards. Okay, let's take a look at the bridge over here. So let me remove all the distractions. For this bridge, if I were to extend it all the way, we see that it opens upwards. Likewise, for the satellite dish, if we were to extend, it is going to keep opening upwards. So graphs with minimum points, they will open upwards. Now let's go on to our workbook, exercise 5.4. We're going to match the quadratic equations to the respective graphs. Okay, so here we've got graphs A, B, C, D, and E. We're supposed to match them to this. So because we're not going to plot everything out, we're going to use a software. So once again, this software is called Desmos. So I've got the graphs over here that I've drawn. They correspond to these graphs shown in your workbook. Okay, then the equations are as such: x squared plus 4, x squared minus 5, x squared minus 1, x squared plus 1, x squared minus 4. So let's take a look at the first graph for x squared plus 4. Okay, do you see which graph this belongs to? It corresponds to graph A. How do we know? What exactly do we look at? So we focus on the y-intercept, where it cuts our y-axis. So it cuts at y equals to 4. So the answer for part A is A. So next, we've got a graph of y equals to x squared minus 5. It cuts our y-axis at negative 5. So we move on to our workbook. The graph that cuts our x-axis at y equals to negative 5 is this, graph E. Next, for the graph of y equals to x squared minus 1, we see that it cuts the y-axis at y equals to negative 1. So we search for the corresponding graph. We see that it belongs to graph C. At this point, have you noticed any relationship between the graph, the shape of the graph, and the equation? Okay, so take some time to think about it. You may pause over here. Now in this green graph, it intersects at negative 1. Notice that this constant after the x squared term is negative 1. How about this? The graph ending with negative 5. Cuts at negative 5. The graph that ends with plus 4, it cuts at positive 4. So make a guess. What should the graph of equation D look like? Did you choose B? Let's take a look. X squared plus 1. Yes, it cuts at positive 1. And the last graph that we have, look at the constant value of negative 4. Looks like it should be graph D. There we have it, it cuts at negative 4. Graph D. So this is all for the work that we will be covering today. Please watch the other YouTube video that I've also included for today's lesson.